right, hopefully everyone can hear me. So I'm Rahul. I'm a grad student at the University of Maryland, College Park. And I also work at Goddard as a co-op as well. And I'm here to present my weekend side project, which was building a balloon payload to do deep learning at the edge of space. And I did bring the payload as well. So if you don't mind just passing it around, you're welcome to take a look at it. You can toss it around or whatever. It's it's pretty simple and we'll go over it. So some simple background is what I'll start with, and then just go over the version 1 of the payload, some flight data, and then version 2, and just talk about the whole process here and hopefully just show off what, an approach to doing this kind of stuff. So I guess before I get too deep into the payload itself, I'd like to talk about what exactly a balloon payload is. And in our case, balloon payloads are low swap testing platforms just, to experiment and find out. Mostly it's an excuse for students at our college to just, take hands-on experience with engineering and just fly something. And actually in that picture, the bottommost payload there is actually the payload I'm presenting, SCAMP. And the thing is, when I went to my first balloon payload launch, which was, wow, 2 years ago, that was a long time. It was really exciting to see all the students, just lining up to like launch their stuff. And I made a decision that I wanted to at least fly something before I graduated. And as a result, I had my objective. I wanted to build a simple balloon payload that can fly, that can do something useful. My ideas got shot down at first until I proposed neural networks because, AI, that was a pretty easy pitch. And then I was like, well, if I'm building this, I might as well just use CFS because that's pretty easy to toss on there. And I had a few Coral TPUs lying around because of some other side projects. So I was like, well, I guess I'll just use those too. I guess one objective I forgot to put here because I'm broke, I need this to be cheap. So the entire payload is actually under $100. So if you ever do want to build something like this, you totally can. It's so cheap, it's crazy. So yeah, and there came my mission statement to build a simple balloon payload that can run any number of neural networks utilizing NASA's core flight software or whatever, and Coral TPUs. So I did the exact opposite. I built the super complicated AI mission payload, which is also known as SCAMP. And this is SCAMP on the flight train, which is pretty much just a rope that carries the payloads up into the sky. And those safety pins are there to ensure that it doesn't fall off and, fall on a car or something, which I think it didn't. So should be fine. But yeah, so going into the hardware itself, it's very bare bones. I took a Coral dev board I had lying around, a simple camera you can get on Amazon for maybe 15 bucks, a power bank I got at a career fair, and then a bunch of duct tape, foam board, and some poster board, and I put together this abomination that is my payload. Interestingly enough, the payload designs that other students had made had a lot of foam to keep everything nice and warm. Later in the presentation, I'll show you that the neural networks actually cooked the board to the point where I didn't even need insulation. So that's why it's very, very open inside. And as for software, I effectively just took a very simple distribution of CFS built off of Draco RC4 because that's what we use a lot at work. So I was like, well, I already know how to use it, so I might as well. Use Linux because a mentor of mine once told me, if you're starting with CFS, just use Linux first, develop your applications, and then move to something more interesting like RTEMS. And over here, I only had 2 apps that were actually like AI enhanced. So we'll go over them in a second, but they were effectively my deep storage application and terrain surveyor. So before we go into all of that, I do want to show you guys some code and kind of walk through the process of how you can kind of deploy these neural networks and do it in a way such that any student can kind of pick it up and fly just on the go. So hopefully my screen is still sharing. Okay. So I'm blind as well. So I always have my things nice and big. So here's a simple Python neural network that I built. Nothing too complex. Anyone who's built neural networks before would not be surprised to see it's just your simple UNet. So you have, actually don't know how well you can see that here. Hopefully that's visible. If not, I'm sorry. But it's just your simple UNet, nothing fancy, nothing complex. The stuff that they teach us in class effectively. So if you took any type of AI class in college, they'll pretty much walk you through how to build one of these. So right off the bat, any student can pretty much pick up, build a neural network and get going. And then the really interesting part, and I guess the hard part, oh yeah, this is just training, is when you actually need to deploy it. So there was this really cool tool that was invented by, I think, Google, hopefully. If not, then well, that's unfortunate. That is called PyTorch to Light RT, which you can just use. It's out there already. It's pretty solid. And what it does is it can take these PyTorch models that you make. So any student who's making a PyTorch model, as basic or as complicated as it is, they can use this tool and instantly convert it down into a TensorFlow Lite model, which effectively takes all of the weights and everything, quantizes it, so that way you can actually utilize it on like edge devices. So it really takes that learning curve just out of there, because you can go straight from PyTorch to this quantized network. And the best part is you don't need any quantization like thingies inside of your training sequence. There's none of that weird math stuff or anything. It's just the same type of neural network you'd make for like a research paper, you can use for this system as well. And that's what I did. So, this is the pip install for that. It does a lot of stuff. And, just let it do its thing. That red stuff is probably okay. And then just import it. And the way it works is you would just provide a sample data set so it can do its distillation. And then you provide optimization parameters. These were all trial and error, but once you figure them out, they're not that bad. And then just converts it. So it'll effectively be something you can just simply export as a TF-Lite model. And then from there, you just do a simple test to make sure you didn't lose too much. Also, this neural network is complete garbage. I made this in 4 hours while gossiping with my friends. So my concentration wasn't really quite there, but that's okay. But yeah, and then after that, that's just a lot of images. The final part that you need to do is if you're using the Coral TPUs, which is what I used for this payload, is you just need to use their Edge TPU compiler stuff. And then that will just compile it down into something that you can then run. So effectively, all students have to do is just provide me their Edge TPU like model, and then we can start running it onto the payload just like that. So that is there as well. I don't know why this thing is in the way. But yeah, and as for the actual deployment portion of this project, which it's one thing to build a network, it's another thing to actually use it. I created effectively a simple library that lets me effectively create an instance of a model. And all I do is just call this inside of a standard CFS app. This is using the sample app, so nothing too fancy, just added a few things here and there. And all you have to do is in a sample app, just, where is my initialize? Oh, here it is. Yeah, so you just need to initialize the TPU. Nothing too complex there. You just provide it the model path that contains your Edge TPU Lite file that will have your quantized and shrunken neural network. And then all of the stuff that happens in the backend is handled by TensorFlow, or I guess TensorFlow Lite. And that takes care of effectively 99% of all the technical work that you need to worry about. The last step is effectively just adding your input and output, which can be done using painful C++, and just invoking your runtime interpreter. And that is effectively just how I pulled this off and how I was able to get it to a point where any student in the club could effectively come in, write a neural network for any experiment they want to run, and then we can fly it pretty fast. But yeah, mostly because we tend to do these 2 or 3 hours before a flight. So procrastination at its finest. But yeah, so that's how that system all works. Guess I'll go back to the slides. Yeah, sorry I'm going too fast on this. I spent a lot of time yapping on the I guess data, so I figured I'll go fast on that part. But so this is a terrain surveyor app. All it was is a simple UNet. We saw a lot of UNets today because it's used a lot. Pretty cool stuff for semantic segmentation. All I did here was just take one off of online on a research paper, and then I just implemented it. And all it does is it tries to look at the ground and see what it's looking at and then classify it. And it does moderately well. For the first 3 flights that I have the flight data for, I used sizes of 256. However, for the future flights that I think will fly on Saturday, that'll be an interesting day. I'm going to be doing a bigger image, 512 by 512, and we'll see what happens. Deep storage is simply an autoencoder that I use to shrink data down completely. So I found that I have like a small SD card, so I needed to save space. So what I did was for every image I took, I would patch it and then shrink them down into vectors and just store them. And then on the ground, decode them later to see what I get. This one, I haven't yet flown, but it will fly on Saturday as well. So those are effectively the 2 big apps that I wrote for version 1, and kind of my approach for how I implemented them. Quantize it, embed it into my CFS system, and yeah. So let's see here. The second flight then was my attempt to collect data on temperature and inference speed, because I want to see how fast I was actually going. Unfortunately, this flight was a failure. What ended up happening was when we were on the launch pad, I gave my payload a nice little pat on the top, and the board is actually a breakout board plus an SOM, and that part fell off. So the payload did not work at all. It was a complete failure, and it did. I mean, it went somewhere. It landed on I don't know who that is, but his property. It was just on the flight report, so I figured it was important. And yeah, so what ended up happening was originally I had the board up here on the lid, which is probably the worst design decision I'd made. And I relocated it in the future. But what had happened was this component up here kind of fell off entirely, which was kind of unfortunate, but that's okay. Because on my third flight, I was actually able to get the data I wanted, and it was a relatively good flight. We got lucky in this one because we didn't land at any trees. We landed in the center of a forest without trees. So it's like the one spot that did not have trees. So that was pretty interesting. And this one was, I feel like it was higher than 95,000 feet, but I think we didn't have the data to really show that, but that's okay. And here was what was really interesting. So this is the flight where I actually learned that my payload was really warm, because as you can see, it never went below room temperature the entire flight. No matter what altitude we were at, it was always above room temperature. And interestingly enough, in the nominal range that the Coral Edge TPU thing datasheet had said it should remain in. And additionally, the inference times remained relatively the same across the entire flight for the most part at around like 5 milliseconds for every single image. So I think effectively I was able to reach 30 frames per second, give or take. But yeah, so that was pretty decent. That worked out pretty well. And that was pretty much the whole first version and that whole system. But I wanted, since I had more time, because that only took like, well, I think 1 or 2 weekends. So I was like, well, I'll try and make it bigger and better because, that's the best thing to do for sure. And that's where I came up with SCAMP version 2, which was effectively take version 1 and scale it up. So I took a Raspberry Pi 4B and I attached 3 Coral TPUs to it. So I want to try doing multiple TPUs against multiple models, see if I can split models between TPUs, just, play around, see what happens, experiment and find out. That's what my professor always says. 2 cameras and a bigger power bank because I needed more power to support this system. The power bank that I got from the career fair, sadly, was no longer cutting it. And I also created a simple standalone payload that effectively could fly on its own called Scamplet, which contains a bunch of sensors that I used for some neural networks that I'll show you in the next slide. Sadly, I didn't really go too much into those networks because that would have been way too much to talk about. But effectively, what I'm able to collect on these payloads on this payload is position, so rho, pitch, yaw, x, y, z, and then humidity, temperature, and altitude. And effectively, I just take all of those and I start using those for my neural networks as well. I also moved to the Raspberry Pi because I wanted to try using RTEMS with these Coral TPUs and just see what happens there. Again, I was just experimenting and finding out. So we'll see what happens once I fly this, which I think I'm also flying on Saturday. So that's going to be a crazy day. And this part is effectively what I did to the software. So I tried to emulate more of a real life like system software for an actual satellite or a CubeSat. So I added a bunch of simulation nodes and I added a bunch of experimental apps down here. These are all just very basic things, nothing too fancy there. I took the deep storage application from version 1. I just moved the code over, so I added it to this payload. Same with the terrain surveyor, and then I added a few new ones. So the first one I added was deep navigation, which will take the IMU data and everything, use LSTMs to effectively figure out the relative position of where the payload is from the starting point. So effectively, I want to be able to create these charts, but without using GPS. So that will be an interesting experiment to see what happens there. And then Secure Inference is an app that I developed to try and do encrypted inference with neural networks. So take an input, encrypt it, toss into a neural network, get an output, then decrypt it and see what happens. The idea there effectively being that, whoever is running your neural network will never see your data. That kind of deal. I'm still working on that one. So we'll see how that goes. And then Bus Monitor is effectively a simple application that will take all of the data on the traffic, all the traffic on the software bus, and then just put that into an autoencoder that will then figure out if it's nominal or non-nominal. And then if it passes a threshold, then it'll flag something. I think there was another presentation that talked about FDIR. I don't actually know what that stands for, but it's the same idea as that. And then finally is deep defense, which is kind of my favorite. The idea behind that one is you have these apps down here and these apps over here. And what they're going to do is play a little game of corruption. So one of these apps will become corrupt and will try and spread just bad data to the other apps that it talks to. And the idea behind deep defense is to try and figure out which app is corrupt and try and stop the flow of corruption across the entire network before it takes over. Effectively, the long short of this is I took a bunch of random CFS apps that were on open source and just tossed a bunch of neural networks in there. And yeah, so we'll see what happens. I should have experimented with this on the ground, but I didn't want to. So I'm just going to see what happens in flight. But yeah. And then some other future work that's going to be happening is, so we have a lot of other payloads in our program. One such is Golden Snitch, which the idea behind that one is a self-stabilizing payload that uses an IMU and those grid fins to make sure that the camera is always pointing down and staying steady. So they wanted to try and funnel their data to SCAMP to try and do some neural network stuff. And same is with Robot, which is literally putting an entire robot arm on a balloon payload. As you can see, we do a lot of fun stuff. But yeah. And the big idea here is I just create a hotspot on the payload so they can send data via, I guess, Wi-Fi. And I think if my payload is still on, you can go on your phone and you'll see a network called ScampNet. But don't bother connecting to it. It's all like static and it'll be, but yeah, very secure. And also SCAMP1 is going to fly on some radiation flights. So we have some flights scheduled to do radiation experiments because of the solar CMEs that are happening this year. So NASA requested that our payload group, along with several others across the country, fly during CME events to just, collect data and see what's going on. And yeah, so that's pretty much all I had. I feel like I might have gone a bit long, but that's okay.
You're right on time. Thank you, Rahul.
Sweet. Yeah.
It sounds like you have a big day coming up on Saturday. We definitely want to hear what happens with your testing.
Oh yeah, for sure. I would be posting it on my website, but I completely forgot to put all of that stuff on the slides, but that's okay. I'll toss it in Slack or something.
Put it in Slack.
Yeah.
There's a chance.
Yeah,
We can take questions.
Questions is good for me too.
No question. There's a comment from Slack, but not a question, that this was amazing.
Oh, thanks.
Please go ahead.
Mhm.
Hello. Good. Hello. Okay. Yes. No. Congratulations. Excellent presentation. The core accelerator you put in the Raspberry Pi. In that case, the Raspberry Pi was running kind of Linux, or you also try with the, you mentioned Artems, no? But I guess it's a little bit more challenging.
So currently it's using Linux. My goal is after this first flight on Saturday, see what happens. And then if it goes well, or even if it doesn't go well, I'm just porting to Artems and we'll see what happens from there. It's all done through USB. So Artems has like the USB stuff and everything. So that should not be a problem in all honesty. I just need to cross compile the TensorFlow stuff into Artems and then it should work out.
Very nice. Very nice.
Yeah.
Any other questions?